This page of notes has an example problem that ties together a lot of the concepts that we've already talked about. So here you're given that it's a block oscillator, right? So it's a spring oscillator. You're given the position as a function of time. Now, anytime you're given a numerical position as a function of time, you immediately want to compare it to our generalized form for position as a function of time, namely x equals a cosine omega t plus phi. Now, notice in this equation there is no phi, right? They just gave us an omega t, so that's 0. So you're always going to want to take whatever function you're given and be able to compare it directly to the generalized form of the solution for the block oscillator. We will also use, and you definitely want to get this down right away, is our omega equals the square root of k on m equals 2 pi f equals 2 pi 1 on the period. So you want to have those equations down in front of you right away to problem solve any numeric simple harmonic motion problem. So take the derivatives to get your velocity and acceleration if you need them, and you will for this problem. But pause the video here, try to work through all of these parts. I realize it's half the alphabet, but I think you'll see the solutions go relatively quickly when you understand how the numbers you're given apply to the general forms of the equations we have, and then you can unpause and I'll go through the solutions with you on the next page. So pause the video here and give it a shot. Okay, hopefully you've accomplished a great deal in this problem, but let's see how the solutions work out. Okay, so as I said, we are going to write down the generalized form for the block oscillator immediately, if that's the system we're looking at. And you can see then right away, we are basically given the answers to A, B, and C, right? Definitely given the answer to A. The amplitude of the oscillation was given as the 4 centimeters. The omega, right, corresponds to the 4 pi right there in our omega t. We know frequency is 1 on the period, and omega equals 2 pi f. So we know the frequency is 2 hertz. 1 on frequency is 1/2 of a second. Omega equals the square root of k on m, so k is our only unknown now. We were told that we have a 1 kilogram mass up here. So now we know d. Throw our calculus into the mix here. So if we take the derivative of our position function, we get the derivative of cosine is opposite sine theta d theta, so that's why we pick out another 4 pi here. So we get a 4 pi. The 4 was the amplitude that we started with, the 4 centimeters. So we get our velocity equation, and then f, the amplitude of our velocity equation, is simply whatever sits out in front of the sine function. And I guess technically that should be centimeters if I left the 4 as a 4 centimeters. So that should be centimeters. And g I have is tricky. Why is g tricky? Well, the maximum velocity is given by our amplitude, so that we know. But if we are asked to calculate at what time does this maximum velocity occur, if we're going to show that mathematically, we recognize that the sine function has to equal 1 when the velocity is max, because that's the maximum value that sine can have, 1. Well, so that will occur at 90 degrees, so pi on 2. So when our angle with the sine equals pi on 2, We have our maximum sine function, so that means t is going to be 1/8 of a second. And since we were given no phase shift in this problem, we started the oscillator off at rest from the position amplitude x max at the right, so it will have its maximum speed when it is 1/4 of the way through an oscillation. So when it comes back to the middle, right here, it has its maximum speed. Then it slows down, half an oscillation, then back, 3/4 of an oscillation, maximum speed again, and then completes the oscillation. So this one was definitely a little tricky. We would plug in our 1/8 of a second, we get x equals 0. That shouldn't be surprising because we know it will have its maximum speed as it passes through the origin. And we're going to continue now to put our calculus into action. We're going to take the derivative of the velocity function. So the derivative of sine is cosine. So the negative stays. We get cosine theta d theta, so that's why we're going to get an extra 4 pi out here, which gives our 64 pi squared. A max is 64 pi squared. And I guess this should also be in centimeters if I didn't change my 4 to centimeters. So A max will occur when the cosine function equals 1, and that occurs at theta equals 0. So that is why we have t equals 0 here. So when we plug t equals 0 back into our position function up here, we get cosine of 0 is 1, so our x max is plus or minus 4 centimeters. So we started at the plus 4 centimeters. When it's at the other end of its oscillation, it's at the minus 4 centimeters, so that represents our amplitude, right? So that's our amplitude. Now, the period of motion is 1 on the frequency. We had the frequency up here, so we have our period quite easily. And if we wanted to know how many periods of motion occurs in 3.6 seconds, we simply divide. So we have 3.6 seconds divided by the number of seconds in a period, so we get 7.2 periods of motion. A period of motion, right, represents actually 4 amplitudes. So that's a little bit tricky. Make sure that you understand that a period of motion is 4 amplitudes based on, let me go back here to what we were talking about. Why is it 4 amplitudes? It is 4 amplitudes because I have a negative amplitude out here, I have a positive amplitude out here. When we started our motion, we were here, so we went 1 amplitude to the center, 2 amplitudes to the other end, 3 amplitudes of total distance traveled, and then 4 amplitudes of total distance traveled to complete the oscillation. So here you have it. Let me again kind of zoom out and clear up my erasures, clear up my marks, erase my marks. So please, make sure you go through each one of these parts thoroughly. We absolutely have the opportunity in class to go over any of it again with you to make sure it is clear.